Welcome to the Bible and Science. This is Dave Prentice. I'm a retired public high school teacher, certified in all branches of science and math. I've also taught on the Bible and Science for many years, both in the U.S. and on many overseas mission trips. This is episode 13 of the Bible and Science. This episode is going to bring out a lot of questions about things that many people just accept as being proven fact. The idea of a Big Bang, for instance. When I was in high school, the single most important lesson I ever learned was from a Jesuit priest named Father Hervé Rasevich. Father Rasevich insisted that we, his students, I was a senior in high school, question our own beliefs. This really goes back to Socrates, the ancient Greek philosopher, or if you saw Bill and Ted's Excellent Adventure, you'd say an old dead dude. But Socrates believed that the unexamined life was not worth living. So the way that Father Rasevich presented it was any belief that would not stand up under questioning is not worth having. So what I'm wondering is, are you willing to question your beliefs about nature and the universe? If you're going to try to deal with the universe, you have to break it down into a number of areas. It's too big for all at once. So I break it down into 4 topics. Number 1, how did matter and energy come into existence? Number 2, how did they get from there to their present state? Number 3, how did life begin? And number 4, once life began, how did it get from there to its present state? Today we're going to talk about question number 1. Matter and energy. The universe is made out of matter and energy. Where did it come from? How could it have come into existence from nothing? Is there a scientific explanation? And then later we'll get to the other questions in later episodes. So let's go back and think of some things we've covered earlier. If you're trying to do science, you start with a hypothesis. It's a tentative explanation for something you observe in nature. And we can't just call a guess a theory. A theory is a hypothesis that's been tested many times by many experiments. It's an attempt to explain why something happens. Now, on the other hand, you have a law that describes what happens. It's also supported by many, many, many experiments, sometimes decades or centuries worth of experimentation. So the theory is trying to deal with why, the law is trying to deal with what. If there's something we can't directly observe, we don't give up, we can use a model. It can be a description, an object, a drawing, a set of equations, many things like that, that helps us get a mental picture of something we can't directly observe. And when we talk about Big Bang, well, there are a bunch of different Big Bang models, but we can't see a Big Bang. We can't reproduce it in our laboratories. Creation and evolution are neither theories nor laws, but models. They're an attempt to wrap our minds around the universe. So why do I say neither creation nor evolution qualifies as a law of science nor a scientific theory? Well, first, neither one has ever been observed. Second, neither one enables us to make accurate predictions about specific future events. We can talk about general trends, but we can't predict specific things, where if you drop something, you can predict how fast it's going to fall because the law of gravity is a law. But you can't make predictions about specific things with creation and evolution. Also, there's no way to perform experiments to test what might have happened in the prehistoric past. Maybe you come up with the right idea, but maybe not. You have no way to know. So either idea, creation, that is complex to simple, or evolution, simple to complex, either one can be modified to account for any possible observation. Neither one of them can be falsified. So when we talk about things like physics and chemistry, those are called empirical sciences. They can be tested by direct experimentation. How about the beginning of the universe, the origin of matter and energy? Was there a Big Bang, etc.? Can you test that? No, that's not something testable by experimentation. So instead, we would say it's part of the historical sciences. Suppose we get it right. Can we be sure we got it right? We can never be completely sure. We could always be overlooking something. So science is always our best guess. Evolution says that things went from simple to complex, overall trend, that there have been unknown natural processes involved at the very beginning to bring matter and energy into existence. Creation, complex to simple, also postulates unknown processes, but these are non-natural processes at the very beginning. Either way, you don't know what the process was. You can try to come up with models, but you can't be sure that you got it right. Speaking of models, how do we set up models? The basic idea behind evolution is initial disorganization, that is simple to complex, and creation is initial complexity, that is complex to simple. We can use those basic ideas to make predictions in as many areas as possible: astronomy, physics, chemistry, geology, and so forth. So we make predictions and we go out and test those predictions to find out which one seems to fit better what we observe in the universe. Whichever set of predictions fits better is much more likely to be correct. Would we say we've proved it? No, absolutely not. But we would just say this is more likely. There's a principle that's used in science and medicine all the time. It's called Occam's razor, named after William of Ockham. He said, entities should not be multiplied beyond necessity. What does that mean? We could paraphrase this to say the simplest explanation that fits all the facts is usually the best. If it doesn't fit all the facts, forget it. But if it fits all the facts, that's a good place to start, a very likely correct answer. It's not a hard and fast rule, but it certainly is a good guideline. The fewer stories you have to make up, the better. So we can make predictions based upon the idea of complex to simple for creation, simple to complex for evolution, in many different areas relating to physics, relating to fossils, relating to genetics and biology and so forth. And whichever one matches what we observe in nature is much more likely to be correct. And I think you'll see as we go through this series, I happen to believe that creation is much more likely to be correct. So first, the universe is here. It's made of matter and energy. Where did they come from? Well, creation says things started in a complex condition, and of course there had to be a creator. So if a creator brought matter and energy into existence, then only the same creator should be able to do it again. And if the creator started the universe at its best, there should be an overall trend toward deterioration, that is, complex to simple. Now, if you believe in evolution, you're trying to explain everything by purely natural processes. So if natural processes brought matter and energy into existence in the first place, then those processes should be able to do it again under the right circumstances. And if things are getting more and more organized, there should be an overall trend toward increasing organization. That is simple to complex. It doesn't mean everything instantly gets more complex. It just means an overall trend ever since the universe began. So prove it. You can't, but we can probably disprove one of those ideas. If you are familiar with thermodynamics, thermo indicates heat, which has to do with energy. All energy can ultimately be converted to heat. Dynamics is how something operates. So the first law of thermodynamics has to do with the quantity of matter and energy in the universe. This is not something that a person just sort of pulled out of the air one day. This is the result of decades or perhaps centuries of observation. And the first law of thermodynamics says matter and energy can be converted from one form to another, but can neither be created, that is brought into existence, nor destroyed, brought out of existence, by any known process. So whatever the process is, it's not known. The second law of thermodynamics has to do not with the quantity of energy, but with the quality of energy. And This is something that everybody's kind of familiar with. Unless it's forced to do otherwise, energy tends to flow from greater to lesser concentration. You don't accidentally burn your hand on a cup of tea and expect it to get hotter and hotter and hotter. No, the tea is going to get cooler as it radiates the heat outward to the surroundings. So unless forced to do otherwise, energy tends to flow from greater to lesser concentration. Doesn't mean it's always going to happen instantaneously, but that's the overall trend. And since energy holds matter together, matter also tends to move from order toward randomness. That is, nature seeks equilibrium. This is not something that was just made up yesterday. It's after centuries of observation. The entropy, that is the disorganization of a closed or isolated system, always increases. If there's no outside influence, it's going to become more disorganized. And so somebody might say, well, maybe God could have done it. Yeah, but that's not a closed or isolated system. You have to rule out every outside influence. And as Darwin wanted to do, explain everything apart from God, well, many others have said that. So the universe has to be a closed or isolated system. So how do we get around the problems of thermodynamics? First law says matter and energy can't come into existence by any known process or be destroyed by any known process. The second law of thermodynamics says that entropy always increases, and as this happens, energy is going to become more randomly distributed, less and less useful. So think back toward the beginning. Right now, the universe has got some percentage of entropy. I don't know what it is, but work backwards through time, it would have had less and less and less entropy, and you would have reached some time in the past where the universe would have been at zero entropy. Well, okay, what happened 1 second before that or 1 million years before that? Known natural laws don't apply. There had to be a beginning. So remember, the idea Darwin had was if you could ever show that there's any one thing that couldn't be explained by natural processes, his theory would absolutely break down. Well, that's the foundation of evolutionary logic. Everything must be explainable by purely natural processes. If you find one thing that can't be explained by natural causes, then all of evolutionary logic is unreliable. If I've told you all dogs bark, how many non-barking dogs does it take to falsify my statement? One, that's all. So I've told you absolutely everything must be explainable by purely natural processes. How many things not explainable by natural processes does it take to falsify my statement? Just one. The origin of matter and energy right from the very beginning cannot be explained by natural causes. So therefore, all of evolutionary logic is unreliable. Well, what if evolutionists find something that can't be explained by known natural causes? No problem. They explain it anyway by making up stories about unknown natural causes. So here's the first story. The quantum universe model. It says, well, okay, in the beginning was nothing. How could you have a beginning with nothing? But anyway, nothing, not even empty space, just nothing. And then the nothing fluctuated and produced a positive universe that we live in and probably a negative universe that we can't detect. This says that the universe is the result of a quantum fluctuation from nothing, not even empty space, just nothing. Of course, this violates the first law of thermodynamics that says matter and energy doesn't come into existence by any process that we know anything about. So we have to say, well, it's an unknown process. But then also, this tries to apply quantum principles that work only for particles of infinitesimal mass. We're trying to apply that principle to the unimaginably massive singularity that suddenly pops into existence and blows up in a big bang and evolves into the universe. I don't think that's valid. Anyway, so how are you going to test this idea that there was a quantum fluctuation from nothing? You can't. And it certainly goes against much of what we've learned about physics through direct observation. Well, what if evolutionists find something that can't be explained by known natural processes? No problem. They make up more unknown natural causes. So here's the next story. The steady state universe. Sir Fred Hoyle came up with this originally, and he doesn't believe it anymore. But this says that the reason the universe is able to continue is there's constantly new matter and energy evolving from nothing out in empty space. You okay? But it's not only empty space, it's unobservable areas of space because we can't see it, so it must be unobservable. So how are you going to test this? There's no way to test this, but it does contradict all of our observations. There are not many people that believe in the steady state universe. Even Fred Hoyle, who proposed it, has abandoned it. So what if you find something you can't explain by known natural causes? Well, no problem. Explain it by unknown natural processes. So here's the next story. This says that there's a cycle of the Big Bang. You've heard of the Big Bang. And then after some extended period of billions, trillions of years, there's a big crunch. It all comes back together. And then it blows up again, another Big Bang, and another big crunch, and another Big Bang, and another big crunch. You could make a song out of that. But there's so much gravity needed to pull everything back together that it would require far more mass than the astronomers have been able to find. And we'll talk about this later with the Big Bang. It requires the universe to be four-dimensional, not three-dimensional as we perceive, but four-dimensional. So if the universe is four-dimensional, where's the center? What? What's the center in four dimensions? We don't know. There would be no center of gravity toward which everything would be pulled. Now, if the universe is three-dimensional, as we perceive, then every time it blows up and crunches and blows up and crunches, matter would be moving at probably near the speed of light, but energy is moving at the speed of light. So some of the energy is not going to be pulled back in. There would be, if there was an infinite number of oscillations, bang, crunch, bang, crunch, bang, crunch, you would have lost an infinite amount of energy. So the amount of energy in the universe is finite. It's huge, but it's finite. So how many times can you add a number together to get infinite? You can't. It doesn't work that way. It's physically and mathematically impossible. So maybe you can push it back through 2 or 3 different Big Bang, Big Crunch oscillations, but ultimately there had to be a beginning where it all came into existence. Remember, the foundation of evolutionary logic is that everything has to be explained by purely natural processes. Well, okay, what's the origin of matter and energy by purely natural processes? We don't have an explanation. That's the fundamental premise behind it, so therefore, all of evolutionary logic that depends on that is unreliable. So we tried natural causes and we can't find any. So what are we going to do? We can't explain the origin of matter and energy by any known natural process. Suppose someday we can find a natural process, which we haven't been able to. We would still have to ask, well, okay, where did that natural process come from? Either God created it or it exists because of random chance. God is certainly not subject to the laws of nature. He is described as an uncaused first cause. Well, if you push God out, you have to appeal to random chance, which also would not be subject to the laws of nature. Random chance would have to be an uncaused first cause. So how are you going to explain God by natural processes? How are you going to explain random chance by natural processes? You can't. Neither one can be explained by natural processes. Either one must be accepted by faith. Well, if it's not natural, it's supernatural. So that was dealing with the biggest question, the whole universe. Where did everything come from? Let's turn our attention to a much smaller question. Where did atoms come from? Atoms make up matter, which makes up the universe. So when we talk about the atoms in the universe, we're talking about things on the periodic table. Starting in the 1800s, people began to put together an orderly arrangement of how the elements that made up everything would fit together. So we have a periodic table that so far has 120 elements on it. 90 of those exist in nature, and the other 30, they've been manufactured artificially in laboratory condition. So we're not worried about the ones that were artificially manufactured. We're concerned about the ones that are known to occur in nature. There are ways to find out what's out in space that we'll talk about in just a moment. And the question is, where did all of these different elements come from? We don't have an exact knowledge of atoms, but we use something called the planetary model of the atom to help visualize it. Nobody believes that this is exactly right, but at least it helps us to understand. Okay, there are these things, they may be particles, they may be waves. Well, they're actually a wave-particle duality called electrons. They move around the nucleus. They don't move in clearly defined orbits, they move in orbitals, which are mathematically defined shapes. And the nucleus is composed of protons and neutrons. Protons positive charge, neutrons negative no charge. So the number of neutrons determines the isotope of the element. We can have hydrogen with varying numbers of neutrons. We can have uranium with varying numbers of neutrons and so forth. So if you take the number of protons in the nucleus, that's called the atomic number, and it determines what element the atom is. The number of protons plus the number of neutrons in the nucleus is called the mass number. That determines the stability of the atom. Now, here's something to think about. Positive repels positive, okay? In the nucleus of the atom, you have positively charged protons and zero charged neutrons. So since positive repels positive, every atom in the universe that has more than one proton should fly apart. But it doesn't. Protons repel each other, but once they're in the nucleus, there's some force that we don't understand that holds them together. What's that force? Well, I don't know. Let's slap a name on it. So we call it the strong nuclear force. We have no idea what it is, but nevertheless, protons do stay together in the nucleus of the atom, and we can use this to determine some things about what's out in space. Each element has a unique arrangement of electrons around the nucleus, and electrons can absorb energy and they can radiate energy. If something radiates energy, energy will translate to colors. So you can see a clearly defined pattern, a spectrum of colored lines as the electrons jump between higher levels to lower energy levels, and you'll see dark lines going from lower to higher as the energy is absorbed. So depending on whether they're being absorbed or emitted, you're going to see either light lines or dark lines. So on the screen there, you can see that's the spectrum that hydrogen produces, and this has been done for well over 150 years. And then if you look at fluorine, it's a different spectrum. If you look at oxygen, it's a different spectrum. Each element has got a unique spectrum, and we can use this to identify that the element is present. So if you're in a laboratory, you can see in the laboratory, here's the pattern indicating that this contains whatever elements. Now, if you point your telescope at a star, you can also see the same patterns that we see here on Earth, and you can tell what elements are in the stars without ever going there. That's kind of cool, isn't it? So in a laboratory, we see an emission spectrum of bright lines against the dark background. In a star, actually, The inner part of the star is so hot, it's so energetic, the electrons are not attached to the atoms, they're just jumping back and forth in something called a plasma. But the light from the interior has to pass through the star's outer regions, its photosphere, on the way to get to us. That part of the star is not as hot, so some of the atoms do have electrons, and they will absorb colors. So what we see on Earth is sort of like a photographic negative. Instead of an emission spectrum of bright lines against the dark background, we see an absorption spectrum of dark lines against a bright background. That lets us know what elements are present in the star's outer layers. We can't really tell on the inside, but the outer layers. So here's how all of this ties in with the origin of the atoms, the origin of the chemical elements. Hydrogen is my example. It has one proton, always. But it's also possible that hydrogen may have one neutron. It's still hydrogen, but we call it deuterium. And there's a very rare form of hydrogen that has one proton and two neutrons. It's an even rarer form, but the question is, could those three forms, the three isotopes, combine to produce the other 89 naturally occurring elements besides hydrogen? These are the naturally occurring isotopes going up to oxygen from atomic number 1, mass number 1, all the way up to 18. And the reason I've highlighted where it says non-existent, suppose we want to put together all of the elements in the universe from scratch. We're going to start with a big bang with nothing but protons. Okay, yes, you can have hydrogen 1, which is one proton, no neutrons. And then it's also possible to put a proton and a neutron, that's hydrogen 2, a proton and two neutrons, that's hydrogen 3. Yes, those do occur in nature. But there's no such thing as hydrogen 4, 5, 6, and so forth. All right, so if you could somehow put together two hydrogens into helium, helium-2, it falls apart instantaneously. Somehow there has to be at least one neutron in there to help hold it together. So there's no such thing as helium-2. But there is a rare form of helium called helium-3. It's one hydrogen 1 and one hydrogen 2. That does exist. But then by far the most common form of helium, sorry about that, is helium-4. So you can get that if you smash together two hydrogen 2s. How about, can you build up the next heavier element? Can you do a helium-5 or lithium-5? No, doesn't exist. We've tried every possible combinations of protons and neutrons. There's nothing that has a mass of 5. It will not stay together. So you couldn't use it as a building block for anything else. While it's possible you could put together two helium-3s to get a lithium-6. And you could also do a helium-3 and a helium-4 to get a lithium-7. Those do exist. We've made those. But then we need to make something with a mass of 8, a mass number of 8. Doesn't exist. No such thing. We've tried every possible combination. There are not that many combinations. We've tried every possible combination. We can't make anything with a mass number of 8 that holds together. Now from then on, beryllium 9, boron 10, and so forth, yes, those will come together. But the question is, can we make these by a big bang with the parts of the universe, the parts of the atoms, the individual hydrogen and helium atoms coming together to make more and more heavy elements? Nope. A big bang could possibly produce lithium 6 and 7, but it couldn't produce any element heavier than lithium. It would be expanding so fast that the particles couldn't hit each other. Why is this such a big deal? Well, somewhere around 99% of the observed matter in the universe, when I say observed, I mean looking through telescopes, doing spectroscopic analysis, about 99% of the observed matter is hydrogen 1 and helium 4. There's not many different ways that you could combine two of those. Try to put together two hydrogen 1s, they won't stay together. Try to put together a hydrogen 1 and a helium 4, nope, they won't stay together. Try to put together two helium-4s. Nope, that wouldn't stay together either. So a Big Bang trying to combine the 1s and the 4s or two 4s, it would have expanded too fast to combine more than two particles at a time. There's no other possible combinations. So we're stopped at every turn when we're trying to make heavier elements in a Big Bang out of the two elements that would have been present. You just can't make anything other than that because you're missing that mass number 5 and that mass number 8, which would be crucial steps to make things in a Big Bang. So what if evolutionists find something that can't be explained by known natural causes? No problem, unknown natural causes. So here's going to be our story. In a star, once all of the hydrogen is used up, it's supposed to experience a helium flash. Suddenly, two helium nuclei fuse into beryllium-8, 3 into carbon-12, and 4 into oxygen-16. Well, here's some problems. First, beryllium-8 doesn't exist. That's purely theoretical. We've tried. We can't make it. It decays instantaneously. It would be unavailable as a building block for heavier elements. Number two, we've never seen this happen. It's theoretical only. It's like science fiction. Even if it did occur, it'd be in the interior of a star and we couldn't observe it. But there's no evidence that it's ever happened, just a desire to have evolution be true. We have to have all of these elements coming together because otherwise we're going to have to appeal to God to make the chemical elements. No, can't have that. And atomic nuclei are so tiny that the chance is extraordinarily small for two to collide, let alone 3 or 4. Well, what if evolutionists find something that can't be explained by known natural causes? Have you seen a pattern here so far? No problem. They explain it anyway by making up stories about unknown natural causes. So here is the story. The Big Bang would have been expanding too fast, and so you couldn't put things together. But let's do it in a supernova. Inside of a supernova, an exploding star, it's supposed to be much, much, much hotter, thousands of times hotter than a normal star. And that would be high enough to smash together the particles and synthesize the rest of the elements. Those are then supposedly flung into space and recycled into new stars. Well, if that's the case, the earliest stars, when I say the earliest, the ones that are farthest away, we look toward the edge of the universe with our best telescopes, that would be the earliest stars. They should have been composed of nothing but hydrogen and helium. And we analyze the spectrum and we say, are we going to see any metal-free stars? Nothing but hydrogen and helium? Nope. We've never seen a single metal-free star, even among those that are the farthest and supposedly the oldest. And then gravity drops off by the square of the distance between objects. It would be far too weak to pull the parts back together and make a new star. So the material should just continually be expanding through space and float forever. There's no evidence that this could happen, just the desire to have evolution be true because we want to get rid of God. So, boys and girls, let me tell you a little bedtime story. The story of the supernova and the elements. Remember, we're trying to explain everything by purely natural processes. What if we can't explain something by natural processes? Yes, we can. We make up unknown natural processes. And because I am so smart, I can make up a story. Therefore, you have to believe me. Okay, here's the story of the supernova and the elements. Supernovae, plural, and the elements. Once upon a time, there was a big supernova. It produced many atoms of heavy elements, but they were spreading through space. Then a second supernova took place light years away. The shock wave from the second supernova traveled many trillions of miles. It pushed the expanding cloud from the first supernova back together into a ball. That became a new star, and now it had heavier elements. The process repeated over and over, and it spread heavy elements to every single star we've ever seen. The end. Yeah, okay. Do you believe that? I don't believe that a shock wave coming across space from trillions, from many light years away, could make an expanding cloud collapse together into a ball again. And I certainly don't believe that this had to happen to every single solitary observable star in the whole universe. I just don't think that's plausible. So remember, the purpose of what I'm talking about right now is to explain the origin of the naturally occurring elements. There are 90 of them, hydrogen plus 89 others, never mind the ones that are synthetically manufactured. We don't have a mechanism to put those things together by any known natural process. We have to appeal either to an unknown natural process or an unknown non-natural process. But if you're an evolutionist like Darwin and so many others, you're not going to allow for the possibility of natural processes. The theory of evolution is accepted not because it can be proved, but because the only alternative, special creation, is clearly incredible. Why? Because it requires God. We can't have God. Got to get rid of God. But think about this. It's commonly estimated that there are about 10 to the 80th atoms, that's a 1 with 80 zeros after it, in the known universe. We don't even have a name for that number. If only 1% are other than hydrogen or helium, 99% is hydrogen and helium, 1% is not. Well, 1% of 10 to the 80th power is about 10 to the 78th power. Quadrillions of quadrillions of quadrillions of quadrillions. That many atoms whose origin cannot be explained either by a Big Bang or by any known natural process. Remember Occam's razor, the simple explanation that fits the facts is probably the best. Which is more reasonable, to believe in one unexplainable event that was not a natural process, or 10 to the 78th power unexplainable events that are certainly not any known natural process? Which takes a bigger step of faith? Creation says one unexplainable event. Evolution says 10 to the 78th power unexplainable events. I have an easier time accepting one because I do accept that there's a God. So this dealt with the first of the four major questions. Can known natural processes explain the origin of matter and energy? And the answer is no. And then in the next few sessions, we'll be dealing with the question of, can known natural processes explain how, whenever it came into existence, it moved to its present condition? That's going to include such things as exploding the Big Bang theory. So stay tuned.